Thanks everyone for coming. My name is Joseph Thiebes, and I'll be talking about developments in time-resolved microscopic characterization of excited state dynamics in semiconducting materials. Today is, as Eric alluded to, a culmination of a lot of hard work over many years, and I want to take perhaps the last opportunity I have here to acknowledge that I've had a tremendous amount of help, without which I would not have the privilege of having done that work or standing before you. I'm grateful to Eric and my committee for their constructive feedback and steadfast encouragement over the years. Also thankful to the whole Grumstrup research group, all these folks, past and present, who've guided me, learned with me, and have been my comrades throughout my time here. Also, these folks, for their guidance and expertise, has helped me to learn and teach and helped me navigate the difficult path of a Ph.D. I've also received funding from NSF, DOE, and MSU. And I also want to thank my parents, whose belief in my abilities, constant support, and love has been the heart of my resolve. And my family, Julia, my best friend and love of my life, shared every joy and every ordeal of this odyssey. And the laughter and bright futures of my children have fueled my resilience. Thank you. So in our group, we use time-resolved microscopy and spectroscopy to learn about structure, disorder, and interactions at the micro and nanoscale and their influence on overall material properties. And these three images here each pertain to different photonic applications. Our work helps to elucidate the fundamental properties and mechanisms that underlie these. So we have solar cells, and this is photocatalysis. This image is from a paper out of our group, and then LEDs, you find them in your phones and your TVs, and we have some folks who are working on analyzing those. So what is an excited state, and what makes it so dynamic? Why do we care about excited state dynamics? Well, this is a cartoon of a solar cell. Light is being absorbed by a semiconductor, and the energy is then used to power a light. But what's happening at the scale of the electron down in here? Let's zoom in. So in a semiconductor, there are energy levels that we call bands, the valence band and the conduction band, and they're separated by a band gap. And that band gap represents the amount of energy that's needed to bring an electron from the valence band up to the conduction band. For those, if there's anybody here's an organic chemist, it's sort of analogous to the HOMO and LUMO of an organic molecule. The gap between the bands of the band gap represents, I already said this. So when there's no excited state, there's no conduction. You've got all your electrons are in the valence band. It's a traffic jam. They're not going anywhere. There's nothing in the conduction band. But when a ray of light comes in, it can excite an electron up into the conduction band. And now you have an excited state. And so that's basically what that is. It's a locus of higher energy in the material. And the electron is in the conduction band, so it can now move around. The hole that it leaves behind, we actually call it a hole. It's just an absence of electron. That can also move around by virtue of the other electrons moving. And so one thing that can happen next is that the electron and the hole are sort of attracted to each other. And if the attraction is strong enough, they'll move together as a unit or a pseudoparticle called an exciton. The charges can also separate, and that's called charge separation. So then those are some ways that they can transport around. The excited states can move as an exciton or as separate charges, but then we have recombination when the electron recombines with the hole, and that's how the excited state relaxes. Once it relaxes, it's no longer useful, so it helps to know how this happens and when it happens. So the recombination, when the electron recombines with the hole, that can produce light or not, and that's just called radiatively or non-radiatively. When it excites radiatively, there's a photon ejected, and that's in particular this recombination happened from the band edge, so it went straight down, and then that photon is the same energy as the energy of that band gap. It can also, instead of emitting a photon, it can put thermal energy into the crystal lattice, which I have symbolized here with a little audio symbol because it's called a phonon. And so that can also happen. There's no light emitted when that happens. You can also have the electron go into a trap state, which is a slightly lower energy. It's a lower energy that's within the band gap. And that's usually associated with a defect in the material or a surface, which is kind of a defect because the material ends. And it's a little bit lower energy, and it can emit from there a photon, and that's called trap-mediated recombination. It can also put the energy into the lattice as heat. There's a third way, which doesn't happen generally unless you have a lot of excited states close to each other. And that's when the electron recombines with the hole, and instead of emitting a photon or putting thermal energy into the material, it puts that energy into another excited state and bumps it up a little bit higher, still within the same band, but a little bit higher, and then it drops back down to the band edge immediately. And that's called Meitner-Auger recombination. And that little bit of energy that it had usually goes into thermal energy. So that's excited state dynamics for you. And so I'm studying all those things that happen between point A and point B, of the light hitting the solar cell, and when it goes into the circuit. In between those is all those transport mechanisms and possibly recombination, although hopefully not much, because that would be lost energy to us. Okay, so after photoexcitation, there's transport as an exciton or as separated charges. And then there's relaxation, which can be either radiative or non-radiative. So how do I study this? How do I look at this? Well, it turns out that when you have excited states in a material, it influences the complex dielectric or complex index of refraction, both of those things. And if you have an excited state, it can be further excited through absorption, and that's transient absorption, when the excited state itself absorbs more energy. Also, just having the excited states in the material can influence the index of refraction, the real part of the index of refraction. You get a decrease in reflectivity. So the bottom line is either you're absorbing more light, or you're reflecting more light or less light, but somehow there's going to be a change in how much light you see at the detector. Whether you're looking at the light that's coming through the material or looking at the light that's reflecting off of it, it will change a little bit when there's an excited state there. And so we can use that fact to make images of the excited state population at the microscale. And we literally do that. And the main method I'm going to be talking about today is called pump probe microscopy. And that is called pump probe because there's a pump pulse and a probe pulse. The pump pulse generates the excited states. It excites the material and creates a whole population of lots and lots of excited states all in one place. And then the probe pulse comes through and takes kind of a snapshot of it. And actually, it doesn't really take a snapshot. It kind of scans over it like this. And so because of the fact that it's scanning over it, we call it spatially separated, because the pump is in one place, and then the probe kind of scans over the whole thing and shows us where the population of excited states is. You can also do it the other way around, but you just keep it like this for simplicity. You can also have spatially overlapped, where you have the pump and probe in the same place, and you scan them both together, and then you get an image of the material and the overall material in its excited state. You can also just keep them in one place, and if you separate the pump and probe by delaying the probe pulse, you can start to build up a kind of a movie where you take snapshots with more and more and more delay between the pump and probe, and then you see the excited state population diffusing out. And if you do it in spatially overlapped mode, as I mentioned, you can scan over the material. And this is a little microcrystal of perovskite, and it's showing it in its excited state. You can also just stay in one place and look at how the intensity of the signal decreases over time. How rapidly it decreases will tell you about how the recombination is happening, because as the population decays and relaxes, you'll get less and less intensity of signal. This is the sort of a schematic of my instrument. Really briefly, I'll show you a couple highlights here. So this is the laser here, and it gets split by this beam splitter. Part of it goes this way, and part of it goes this way. This side becomes the pump, that's why it's blue. And the pump goes through and then eventually goes to the objective here, which focuses it onto the sample. And then it passes through and then goes to the detector here after getting the red light filtered out, which the red light is the probe. And you notice it kind of follows a similar path, but it has this difference here where it has this delay stage. And basically these two mirrors can move back and forward and change the path length of the probe beam and thereby change how long it takes for the probe to get there. And so you can separate the pump and probe in time and get that movie. Okay, so today I'm going to be talking about, well, my dissertation has four main topics. The photoluminescent redshift that we observed in perovskite bulk material. Also, we did a kind of a comparative study of ligands in perovskite nanocrystals. I did a project looking at the impact of noise on these measurements and quantifying that. And then finally, did a study on a new photocatalyst material and how it has a facet-dependent charge separation. So those are the four topics in my dissertation. That's a lot to talk about in 45 minutes. So in the interest of time, I'm going to kind of drop that first topic and just talk about these three today. So first, I'm going to talk about ligands in perovskite nanocrystals. So just to tell you a little bit about perovskite first, it's initially was a mineral. It wasn't discovered by Perovsky, but it was named after him by the person who did discover it in 1839. And it's an insulator. The mineral that occurs naturally is an insulator, but it's of interest as the perovskites that we look at are semiconductors, and they have the same crystal structure, which is why they're named the same thing. This is the mineral calcium titanate, which is a mineral oxide. The ones that we look at are mineral halides, or really just metal halides, and they have this formula of ABX3, where the A is a monovalent cation. It can be cesium, or it could be their methylammonium and formamidinium, which are sort of organic moieties that have a -1 charge, or +1 charge on them. And then the B is a divalent metal like lead or tin. And it's octahedrally coordinated to the halide anion. You can see those octahedra here. That's the lead, and then the gold spheres are the halide, in this case bromine. And they share the octahedral corners. These are some examples of halide perovskite: cesium lead tribromide, methylammonium lead tribromide, formamidinium tin iodide. And these there are a number of applications for these, which include solar cells, LEDs, and lasers. They're interesting because they're easy to make, they're inexpensive, and they have, we can swap out all these different elements. So there's a really rich field of chemistry that we can look at with these and see how they behave with different constituents. And they're very useful for solar cells. That in the space of about 10 years, they are already competitive with silicon in terms of their efficiency. And the only problem with perovskites is that they are sensitive to degradation by exotic things like water, oxygen, and sunlight. Maybe a little bit of a problem for solar cells. But perovskite nanoparticles can kind of address this problem. The synthesis of these nanoparticles involves using ligands, which are these. This is an example of the kind of molecule you can use, if I can find my pointer, that you can use as a ligand. And they put that in the synthesis process so that it kind of stops the crystal growth when they're still very small. And these ligands are hydrophobic, and so they protect the crystal from degradation. This is the prototypical perovskite nanoparticle was synthesized by Protesescu and coworkers. And they used these ligands: oleic acid, which you find in olive oil, and olelamine, which is the sort of the same backbone, but has the amine group instead of the carboxyl moiety. So the functional groups attach to the polar surface of the perovskite, while the tails are hydrophobic. They protect against water and oxygen. However, they're also insulating, so they tend to inhibit energy transport. So it's hard to get transport of energy between nanocrystals. So we had this hypothesis after seeing some work by Vickers and coworkers. They were looking at photoconductivity using conjugated ligands instead of those aliphatic ones. And they found that there was some increased conductivity between nanocrystals. And so we had this thought that maybe the conjugated ligands can facilitate delocalization of the excited state and lead to faster diffusion of excited states through the array of nanocrystals. And so this diagram here, it's kind of like the particle in a box toy system that you have. You've got your wave function, and it's sort of isolated by this barrier, which is just the space between the nanocrystals. And these aliphatic ligands are not going to help to move any energy around. But our hypothesis is that if we use these ones we've got conjugation and these aromatic rings, we may be able to delocalize the excited state and lower those barriers to transport. So just to recap quickly before I get into how we looked at this, time-resolved microscopy, we've got this, again, this movie where we see the excited state population diffusing out. And we can take a cross-section of that, or we can also integrate it in one dimension. And we can see that basically the height of these peaks is the intensity. And over time, that sort of bell curve spreads out and diminishes. And using that, we can calculate how the diffusion is going, how quickly it's moving, how quickly the excited states are moving through the material. And also, if we just take each of these time slices and consider, sort of plotting it in a different way. That's what we've got here in this rainbow plot. And so basically the red part is the top of that peak, and the blue part are the tails of that. And so this is plotted over time. So if you look at a slice at the bottom, that's at time 0. And as you move up, you're moving forward in time. And so if you have diffusion, then this peak you should see it spread out. And in this plot here, you can kind of see a little bit, if you squint your eyes, maybe a little bit of that happening with this other ligand, the TCA DPPA, which is the conjugated ligands. And so did some other analysis. This is maybe kind of a qualitative view of it, but if we plot the mean squared width of those Gaussian functions, we can see the width of them increasing linearly, roughly, over time. And then we can get the slope of this line, and that's proportional to the diffusion coefficient. And for the oleic acid olelamine one, it's this number, which doesn't mean a lot just out of context. But if you look at it in comparison to the conjugated ligand is about twice as big. So we're basically seeing diffusion in this particular example that's about twice as fast as in the original prototypical system. So that was encouraging. So we did a bunch more experiments, and we also looked at the kinetics, this is again that decay where we just look at it in one spot and watch how the intensity of the signal decreases over time. So we're seeing the relaxation over time. And we would expect that if they are delocalizing, there are going to be more interactions between excited states, which may increase the rate of recombination. And we do see that here in these kinetics, where this is happening slower than this. So there's an increase in the speed of rate of recombination. So we took a bunch of diffusion measurements on these, and this is about 8 for each system. And this is a histogram of the diffusion coefficients that we calculated from each one. And so it kind of looks like, in almost all the cases, the conjugated ligand, the TCA-DPPA one, is diffusing faster. So this was very encouraging. And we started thinking, well, gosh, we really have something here. The diffusion measurements do consistently show faster transport in the conjugated ligand nanocrystals. The faster decay shows increased recombination rate, which we'd expect. Both the above findings suggest that we've got pi bond conjugation and aromatic rings facilitating that wave function delocalization. And the conjugated ligands, for engineers, they can be be used to strategically enhance optoelectronic properties. And that encourages exploration of other conjugated ligand systems for optimized materials. And I've got ideas, by the way. So the next step, we could try something that's conjugated and Switter ionics, because that would have the ability to kind of use a bidentate mechanism to connect to the nanocrystal. But hold on. I started looking at this data. And some of these measurements, I was looking at them and thinking, I don't know. I started looking at these error bars, and these ones are all right. But then when I look at this confidence interval shaded area, like the bottom of that is almost at 0 diffusion. And these error bars, this is sort of a different fitting method. These error bars are huge. So how much noise can we really tolerate in these measurements? I started wondering and asking annoying questions in group meeting every time. And eventually, I think, Eric said, I don't think anybody's really thinking about that. Let's do some simulations. So that brings me to my second project, which is quantifying the impact of noise on measurements of diffusion. And so just again, a quick recap, we photoexcite a population of excited states. And then that laser pulse, the intensity of the laser pulse is going to be proportional to the population of excited states. So if the laser pulse is well characterized by a Gaussian function, then so too will the excited state population be. And that has been found to be the case. If you have a well-focused laser, you will have a Gaussian approximate distribution of excited states. So we can, in calculating the diffusion coefficient, first step is to fit each profile at each time point to a Gaussian function. Again, either taking a slice or doing an integration in one dimension. And then we fit those, so you see this blue line is showing the data itself, and that's represented also by these blue dots, and then the gold line is the fit to the data. And then we get the width of that Gaussian at each of those times, and the square width scales linearly with regular diffusion. And that's shown here. So as the population widens, and we're normalizing the height at each time step, so that as it widens, the square of the width goes up linearly, and that's proportional to the diffusion coefficient. So that's how we measure diffusion. So my question was, how much noise in those measurements can we tolerate? If we look back at this one, you can see the blue dots aren't exactly on the line, right? They go up and down, there's some noise. Well, how big can that variation be before we start to really have questionable results, is my question. So I have this hypothesis. Under a given set of initial conditions, we can predict the reliability of diffusion estimates. Okay, so we start with an initial population width, and an initial diffusion coefficient that we're just going to assume is true, and we're going to plug that into a simulation to create sort of noisy Gaussians. And we also come up with a decay lifetime and an initial contrast to noise ratio. How much noise is there at the beginning? And then the resolution of our instrument, we can kind of look at, do we have 100 pixels across? Do we have 500 pixels across? And then how many time frames do we take, and over how much time? So using those initial conditions, we can kind of try to predict what the noise how the noise is going to impact our measurements. And this was kind of an early simulation I did just as an illustration. And so this axis here is time. And so back here at time 0, you have this tall peak. And then as time goes on, it spreads out and diminishes. And it's undergoing both diffusion and decay, right? So, and both of those things are decreasing the actual height of the peak. And over time, it drops down, and this black plane is something I just put in there artificially to say, okay, this is the, what we learned in instrumental analysis, the limit of quantitation, so to speak. And so as it drops down in here, we can start to see that more and more of the peak is dipping down into that below the level of quantitation. So I started asking, at what point do these measurements start to become questionable? And this is really, you know, if you were to normalize these peaks, the noise would get more and more intense because the noise is becoming more and more prominent and more impactful as time goes on in this measurement. And that was really a big part of my question, because if you look at these, sorry, I gotta back up. If you look at these, like these error bars represent the error of each individual time frame. That's the uncertainty of each individual time frame. And then we have a plus or minus value here, which is related to the slope of this line that's fitted. So those are two sort of separate uncertainties that I don't think they really capture the fullness of the uncertainty. So back here. So to do the modeling, basically I generated a series of time-evolved Gaussians with a given set of initial conditions, and then I added noise to them. And then I fitted them and compared the fit to the parameters that I input. And so we start with these initial conditions, the population width, the diffusion length, which is, it actually kind of combines both the diffusion coefficient and the lifetime into one parameter, and we can use that generalized so that, you know, any combination of these two that adds up to, or that multiplies and square roots out to the same diffusion length will give us the same results in terms of how quickly the contrast is lost in the signal. We start with initial contrast to noise ratio, which is the peak height at time zero relative to the standard deviation of the noise. And then we have some parameters for spatial and temporal resolution, how many pixels we have, how many time frames we have. So I generated time-evolved Gaussians, added white noise to them, and then fitted them and compared them. So the question was, how do the estimates of the diffusion, the fit, how do those compare to the nominal value that we put into the simulation? And what portion of the fitted values are within 50% of the nominal one? And so we did 2 million simulations with a variety of different diffusion lengths. And we put the diffusion length in terms of the initial full width half maximum, and that made it so we could generalize for whatever your initial full width half maximum is. You can calculate the diffusion length in terms of that, and this plot will be sort of generalizable in that way. So this goes from about diffusion length of 0.001 to 2. And then we have the contrast to noise ratio on the x-axis, and that goes from about 3 to about 100. And the contours here represent the portion, the percentage really, of the fitted diffusion coefficients that are within 50% of the nominal parameter value that we put into the simulation. And as you would expect, if you have high contrast to noise and fast diffusion, you're going to get pretty good fits. You know, 99 or more % of them are going to be within that 50%. And as you start to go this way, though, you find that it drops off really quickly. It doesn't take very long to go from 99% to 25%. As you either decrease your contrast to noise ratio or you have less and less diffusion. Because as you can imagine, if you start off with a peak that's this big and you end with a peak that's barely perceptibly larger, but you can see your noise, then it's going to be hard to really get a good grasp on how quickly that diffusion is happening. So this parameter space here covers the vast majority of published results that we've seen. And we do see stuff down in here and we see stuff up in here. But the interesting thing was, as I was, you know, kind of asking this question of how much noise can we tolerate in our experiments, I started looking in the literature, of course, to find out what other people had said about that. And nobody had said anything about it except that noise limits our ability to get these values right. But nobody had quantified it. I couldn't find an answer to how much noise can I have in my measurements and have it be reasonable. And so this is really kind of the first time it's been quantified. And so we have this map to kind of give people an idea, a rough sense of things. But also, by the way, there's dragons down here. Down in the lower left corner, not only do you get really poorly fitted diffusion coefficients, but they're actually biased so that you actually get diffusion coefficients that can be a lot larger than they should be. And the bias at extreme low contrast to noise and diffusion length estimates can be more than an order of magnitude too large. And this is just showing the sort of the average estimates. And each of these data points is, I think, 1,000 simulations. Average estimate versus the nominal value that we put in. As you can see, the average starts to creep up. It should be down here at 1, but it's creeping up to 10 up here. And actually, if we go a little bit further this way, it shoots way up to 80, 100, 1,000. So they get way too big really fast. And this is just a function of the fact that you can't have a Gaussian with negative width. So you get kind of, you come up against the limit of what the model can do. So you start to get these biased values. And this is important because there are cases where people are trying to take measurements with low contrast to noise and small diffusion length. And also, if you average biased measurements, you're still biased. So if people take the measurement 10, 15, 1,000 times and average their results, it's still going to be biased. So this really kind of says, hey, you can't do that. You have to average your data first so that you can increase your contrast to noise ratio before you can really do that fitting. So some other proposed strategies for folks if they find themselves in a situation where they're getting poor fits. Of course, you can increase your initial contrast to noise by improving instrumentation. Wouldn't that be nice? Or you can take multiple measurements and average the data in order to increase your contrast to noise. You can, let's see, if you have slow diffusion, you can take data at later times to increase the total displacement. You can also increase your spatial or temporal resolution, although that doesn't improve a whole lot. It goes as root n. So it can help a lot if you're doubling your spatial or temporal resolution, but you have to get pretty high before you like trying to get off of this rail down here is pretty hard because, as you can see, this is a logarithmic scale on the contrast to noise. And so, you get out to 1,000, this line is not, it's linear in this scale. It's not, it doesn't come down that far. So, so that may or may not help in your situation. But because everybody, every researcher has different situation, different instrumentation, different contrast to noise, different reasons for doing what they're doing and different levels of tolerance for, imprecision, I created this software tool which basically does the simulations that I was doing to do this study. And people can put in their own parameters and run it. And it'll give them this result, which just basically shows the fitted diffusion coefficients and how far they are from the nominal value. And it gives you the mean, standard deviation, and mode. So you can see if there's skew, if there's bias. And this is open source, so people can improve it, use things other than Gaussian fits or, diffusion models that are not linear. And there's some folks using it. So revisiting the nanocrystals, now that I've done this study, I went back to the nanocrystals and said, okay, well, so how was my signal to noise or my contrast to noise, and how precise are my fits? And so what I found, here's just one example where I did a Gaussian fit, and then I looked at what's the 95% confidence interval of that fit, and it looks kind of big, and that was kind of what I was concerned about. But then when I do the fitting of the diffusion coefficient, I think I did 10,000 fits here. And as you can see, almost all of them are within 50% of the nominal value. So if that was my level of tolerance for precision for that particular experiment, which I think looking back at those histograms, this is pretty good. And so that was encouraging. Great to see that. And I think we're gonna maybe, folks following me will do some more work in that respect. So that brings me to my third topic here, which is the facet-dependent photocatalysis that we see in this sort of new photocatalyst material which are the bismuth oxyhalides. In particular, the one that we look at is bismuth oxybromide. Let's see. So bismuth oxybromide, Paul Goosley helped us, and he synthesized these and did this SEM, did a terrific job. You see, these are also colorful. This is actually thin film interference that we see in the visible light microscope. So this is like, if you see, oil on water and you see the rainbow colors because it's such a thin film. It's the same thing happening here. You have these very thin, flat platelet crystals that interfere with the light. And so depending on how thick the crystal is, you get different colors. So if you look at them without that, nice microscope, you just look at them in a pile on the table, they're white. But they're kind of cool like this. And so this is the SEM. You can see the characteristic, rectilinear shape of these. This one on the right, these oblique angles are because they're sitting at angles. You're seeing some perspective there. They're actually, these are right angles. And you can see they have this sort of flat, thin appearance, and that has due to the crystal structure. And these have been found to have charge separation through the internal electric field of the material. And there's basically an internal electric field that within the material, it all cancels out, but at the surface, you get some band bending. And so at some surfaces, the bands bend up, other surfaces, they bend down, and because of that, you can get charge separation. And you have the electrons and holes get transported to different crystal facets, and then you can do different kinds of chemistry in those different facets. And so we thought, well, using our spatio-temporally resolved spectroscopy and microscopy, we can maybe see this charge separation somehow. And so this is the structure. As you can see, it looks well. This is kind of like a hamburger, right? There's layers, and in between these layers, there's just van der Waals forces holding these layers together. And if you look at it from the side, there's the gap between the layers there, and these orange or gold spheres are the bromines. The purple ones are the bismuth, and the reds are the oxygens. And looking at it from the top down, you can see that it has this very rectilinear structure. This is the unit cell here. And so when we look at the different crystal faces in terms of where the electrons and holes go, there's kind of two main classes of the crystal facets that we're looking at. There's the 001 face, which is the large flat face that we saw in that SEM image. And then there's the lateral side faces, which if you were just cut it down the sides, that would be what you get. And so these are the 110 and the 100 family, or 100, 200, 300, and so on. And those are basically these cuts. If you were to look at it from the top down and cut them in these ways, those are the faces that we're looking at. And so also Paul did this XRD, which shows really intense peaks for the 001, 002, which is the large flat faces, 003, 004. Those are all the large flat faces. There is one peak that is super visible here that is the 110. It's pretty small. I think there's another one over here that's it's too small for it to show up on this graph at this size, but those are the lateral sides. And the reason that there's such small peaks, we surmise, is that the way that they're deposited on the glass for the XRD, those surfaces are vertical, which is not going to produce very much reflection of the X-ray. So we're not seeing very big peaks there. Also, they're a lot smaller surface area. So both of those factors are going to lead to small peaks. So the hypothesis that we had, well, this is what the researchers found, was that using sort of a photo deposition approach, they found metals would deposit on the 001 faces at the edges, along the edges here. So, and then they found that there's evidence for the holes going to the lateral sides. And so this is my kind of version of this drawing. It's a little bit more cartoony, but it shows the crystal structure underlying what we're seeing here with the band bending going up on the 200 or 100 faces, and or 110 for that matter, and then the 001 is where the electrons go. And so you can do reduction on this side or oxidation on the lateral faces. And so we just started looking at what we would see. And so this is a pump probe image of a crystal of this bismuth oxybromide. And then I have two sites where I took kinetics data. So we're just looking at how the excited state decays over time. And I just kind of highlighted the number of merit to look at here, which is that, oh, that should say B, I'm sorry. So in this case, this is A, this top one, and that's sort of the edge/corner. And that has this lifetime of about 2 nanoseconds. One in the interior is less than half of that lifetime. And this wasn't just one set of data. I looked at a bunch of these measurements and looked at, kind of thought, well, how do they compare at other edges, and looked at different crystals. And I kept seeing that there were much longer lifetimes at the edge than there were in the interior. And that would sort of go along with having separated charges, because if they're separated, it's harder for them to recombine. And so they won't do it as often. And so you'll have longer lifetimes. So in order to avoid the possibility that I was just getting lucky, we started doing excited state lifetime imaging, which is where we basically took a lifetime measurement at every pixel on the crystal and then mapped them. And this is the first result here. And so we have these are crystals, and these are lifetimes that we measured at each place. And this is of the 2 lifetimes we fitted. This is the second one, the longer of the 2. And you can, it's visually obvious here. There's, it's yellower along the edges, and that was encouraging. But being I want to say persnickety, but as picky as I am about making sure that the noise isn't confusing us, I wanted to make sure. And also, I thought maybe we can do kind of a do a plot that shows the lifetime as a function of distance to the edge. And so, the thing that I did was develop a way to relatively quickly, find where the edges are and record it so that I could then easily do analysis, because I didn't want to go through 10, 15 crystals and hand draw in where I thought the edge was. So I just made this little app. Let's see if I can, just made this little app using Python. And let's see if I can. So there's the app. And so this has the pump probe image here. And I can basically adjust the gamma, which is kind of like the brightness of the image. And I can adjust how much it sort of denoises the image. And on the right, you see this red border, and it updates live to let me kind of see, get it to pick the edges. And I want to emphasize here, I'm really doing the deciding about where the edge ends up. I'm just using this as a tool that's easier than sort of hand drawing it. And so I get something that looks pretty reasonable, and then I save it, and it does a preview where it shows me, what the original looked like, where the crystal area I picked is, and what it looks like if I overlay it. And if I decide that looks good, then I save it and go on to the other analysis. I did this fitting, and I basically, just to get a quick view, I did an average lifetime where I took the amplitude and weighted the lifetimes with the amplitude. And then I got the error out of the fitting for all the parameters and propagated that error to the average. And I said, okay, if the 95% confidence interval, the lower limit of that interval is less than 0 or equal to 0, throw it out. So I didn't want to take anything where the fit was not good. And so what you see on the right here is one of those lifetime images, and basically everything that's white is a pixel that got thrown out because the fit didn't match my criteria. And all of the pixels that are colored are within that 95% confidence interval. It's all above 0, and it gives us the lifetime. And then down here I have the lifetimes, and I have sort of binned them just because there's a lot of data points. And then the dot and the error bars here are showing the average and 95% confidence interval for that average of that bin. And then the line this is really just a qualitative linear fit to kind of give you an idea of the trend. But that's on the underlying data. It's not fitting the bins, it's fitting the underlying data. And there is, you can't see it here, I don't think, especially on the projection, but there is a yellow shaded area that shows the 95% confidence interval. In this case, it's very close to the line. And the gray pixels are outside the crystal area that I determined with that little app. White pixels, the fit was poor. There are many poor fits, and there's some, which you'll see in a minute, that are even worse than this. It's just due to the inherent challenges of the measurement procedure, where I had to balance, basically, there's weak signal if I have low excitation fluence, but I get sample damage if I have high excitation fluence, and finding that balance was difficult. And so some of the measurements, I just had a lot of noise. Taking this measurement and looking at these trends, it's pretty clear from across all the samples. There's an upward trend in all of these, no matter how few of the fits are good. In this case, I only had 2 data points, so I didn't fit those to a line, but they still have that same trend. This one is a shallow increase, but it is an increase. And this one is really good. It seems like the more data points I have, almost the better the fit ends up being, which makes sense. So the conclusions I have about all of this work, I think that I helped to advance the understanding of excited state dynamics in facet-dependent charge separation in bismuth oxyhalides and ligand influence on excited state transport in perovskite nanocrystals. I think I also helped to advance the field of time-resolved microscopy by developing new standards for reporting diffusion measurements, and some folks are using that software that I made to actually report in their papers what their contrast to noise is, and how their fits perform if we use a simulation like that. So thank you very much.